So we now look at the interval definition of a solution. So I want to take you back to your calculus when you were learning about functions, where the emphasis was for a function to be defined, you need to specify the domain. And of course, to specify the domain, you started with the maximal possible domain and then look for points that are not allowable in that domain and take them out to get the appropriate domain where the function is defined throughout. So those functions that you looked at before, or some of them, they are actually solutions of some differential equations. So the same aspect of defining where the function is defined is what we want to look at, and except that in this case we just don't call it a function, we call it a solution. And of course we're going to look at a function in the first place. So what is the interval definition of this function? So this is a function that probably you saw before in your life. And of course, if you did some curve sketching, you basically could see that the function could looks like this one, that graph that you see there. And of course, if we're looking for the domain, we start with the whole real number line. And then we say, look at the function y there. At what points is the function defined and at what points is the function not defined? And of course, we don't want the numerator, the denominator to be equal to 0. So all points where the denominator is equal to 0 are the points that we don't want in the what? So x squared should not be equal to 1 for this function to be defined. So we then take out the points -1 and 1. So what would have happened now is we have this space, this sub-interval from -infinity to -1, followed by that sub-interval, followed by that sub-interval. So we have 3 sub-intervals. So then you then say the interval of definition I, remember we just say it's called I, is actually equal to this interval that excludes 1 and -1, or you can write it in that other form. So that's what we were doing. So we're just looking for those points. If y is just a function that we want to define its domain and draw the graph of that function, then we will end there. Just look at those points that are not allowable in the maximal domain and take them out. So if you take 1 and -1, then you have the rest of the points as the domain or the interval of definition. So it will be a union of sub-intervals in this case. Now let's look at if now we talk of interval I of definition of a solution of a differential equation. So now we have this differential equation, and then the question is solve this differential equation and find a solution. And the solution also will be y of x equal to something. And of course, if it's now a solution, then what we will need is we're looking for that interval where the solution y should be 1 defined and 2 differentiable. And we're looking for the largest possible interval. And like before, you start with the what? With the whole of the real number line. And then now you search for points that are not allowable in the solution. Now, if you solve that equation, you'll get this solution here. Now, you see we have a potential. C is just a real number here. We have a potential that C can be 0, C can be greater than 0, C can be less than 0. So we now want to check what happens if c is less than 0? What happens if c is greater than 0? So if c is greater than or equal to 0, then we have to make sure that x squared is not equal to c. Otherwise, the solution is not defined. So in that case, we'll then have to say x should not be equal to plus or minus root c. That's our solution. Those are the points. But now let's look at that root c. Now, if c is greater than or equal to 0, then this square root is defined. But if c is less than 0, we have a problem. Okay, now for this one, okay, now let's do it. Let me take it again. So if c is greater than or equal to 0, then we don't have a problem with the square root. So if c is greater than or equal to 0, then we have x should not be equal to plus or minus square root of c. Okay. So then we take our interval for that case. I would be minus infinity to minus root c union minus root c to root c union root c to infinity. That is if c is greater than or equal to 0. But if c is less than 0, we are no longer talking of this. We're now coming back to that one. Then x squared minus c is always greater than 0. So in that case, if any value of x will make the function, the solution defined. So in that case, you are just going to take the interval is equals to the whole set of real numbers if c is less than 0. So that's all we need to do. And of course, this solution is differentiable. All right, so that's what we do when we're looking for a solution or the definition of a solution of a differential equation. So it should be defined and differentiable. Now let's look at a interval of definition I of a solution of an initial value problem. So basically, you have the differential equation and then you add some starting point. So now what it means is you have to solve. If you solve this initial value problem, then you will see now that the c that we had there is actually equal to 3. Now, obviously, this function cannot be differentiable cannot be defined and differentiable when x is equals to plus or minus root 3. So we don't want x squared to be equal to 3 in this case, which implies that x should not be equal to plus or minus root 3. So then if we were looking at this without the initial conditions, then we were going to just say our interval is minus infinity to minus root 3 union minus root 3 to root 3 union root 3 to infinity. Okay, but look, because we have asymptotes here, not all the parts of the sub of this interval should be the intervals we are looking for. So for example, we have our minus root 3 here, and we have an asymptote at root 3 here. We have a solution there, we have a solution here, we have a solution there, minus 1 over 3. All right. So now we are saying when x is equal to minus 2, so minus 2 is on this part of the graph. and y is equal to 1. So we are basically looking at this solution here. So because this solution, there's no way this solution will cross over into this region, into the other region. So the specification of the initial condition will then restrict us to the solution that is just in this region here. And nothing else. We can't talk of this one. We are only talking of this solution here. So then I is now restricted to the interval. So y in this case will not be an element of minus root 3 to root 3. And y at the same time will not be an element of root 3 to infinity. Why? Because it's restricted. The solution on that region is restricted by the asymptotes. Y is x is equals minus 3 there, minus root 3. And the solution cannot jump to the other one. In any case, if it jumps, then it's no longer differentiable. So this is the only region that we will then restrict. So initial conditions have a potential to restrict the interval of definition of a solution, depending on the problem. So it depends on the type of solution that you have. But in this particular case, where you have rational functions, the denominator definitely will affect how your solutions will appear. So you will have pieces of solutions which occur in different subintervals. So when you then restrict some initial conditions to a specific point on the domain, then the solution will be restricted to that specific subinterval. But it depends on the type of problem. Sometimes you find that specifying the initial condition, it doesn't affect the interval of definition of solution, especially if the interval of definition is the whole of the real number line. So specifying the initial condition will only restrict you to the one solution curve that passes through that point only, but not necessarily the interval of definition of solution. All right.